This is Sui HotStore, a local key-value serving layer built for Sui's read-hot path. In plain terms, it loads Sui data into key-value storage, then benchmarks the same schema on RocksDB and ToplingDB. In this video, I want to explain it with real benchmark data. Let's start with why it exists. If you look at apps on Sui, indexers and RPC services tend to ask for the same kinds of things again and again. Fetch a transaction by digest, fetch an object by ID and version, scan events by type. Under the hood, those are all give me a key, return a value, but full node storage is designed for consensus and the state machine, not specifically for this read-hot path. There's room to do better there. So HotStore has a very specific role. It is a benchmarkable key-value hot path. It is not trying to replace a full node. We import a bounded range of Sui data, encode it into key-value records, and run RocksDB and ToplingDB against the exact same schema. The target users are teams running their own indexers, RPC providers, Explorer and Wallet backends, and analytics or archive systems. Right now, the focus is import, key encoding, dual backend comparison, checksums, and benchmarks. The architecture is intentionally straight line. Data can come from three places: checkpoints pulled from mainnet RPC, a prepared real-world dataset, or synthetic data. All of them go through the same bounded range import pipeline into a storage abstraction layer. That layer is the key point. RocksDB and ToplingDB sit underneath it, but the interface above is the same. Below that are 6 column families for transactions, objects, events, and related indexes. Off to the side, one toolchain validates data, the other runs benchmarks. Here is the schema in more detail. The 6 column families match several common Sui access patterns. Keys use big-endian encoding, so range scans stay ordered. For scale, there are more than 2 million rows in object versions and owner-to-object indexes, over 800,000 events, and more than 500,000 transactions. This is not toy data. It was exported from real mainnet checkpoints. On the engineering side, the read path has a few concrete optimizations. First, the two backends are swappable, but the schema-level behavior stays identical, which makes the comparison meaningful. Second, reads are zero copy where it matters. Get and multi-get use pin slices and callbacks so they can read the underlying value without an extra copy. Third, column family handles are cached at open time, so the hot path does not look them up repeatedly. Add deterministic key encoding and per column family checksum validation, and the benchmark numbers become reproducible. Before the results, here is the methodology. The dataset is a slice of mainnet checkpoints with 67 million records. The test machine is a Linux server with a Xeon CPU and 135 gigabytes of memory. Each workload runs 2 million requests after 100,000 warmup requests, with concurrency sweeping from 1 to 64. The 7 workloads cover point gets, batch gets, prefix scans, and a mixed RPC profile. The order is fixed. First, prove both databases contain the same data, then measure throughput and latency, and only then look at memory and disk. Now, throughput in point get, batch get, and mixed RPC workloads. ToplingDB's peak throughput is roughly 2.6 to 3.9 times RocksDB's, averaging a little over 3 times. The fastest workload, get last seen, reaches more than 13 million requests per second at concurrency 64. But I have to call out the exception. On the far right, scan events is faster on RocksDB. I will explain why later. Because this is not something to hide. The latency gap is even easier to see. This chart shows P99 at concurrency 64. For getTX, RocksDB is at 0.95 milliseconds, ToplingDB is at 0.01, about 1/8 as much. For get last seen, P99 goes down to 6 microseconds. The largest gap is in the batch read workloads. Once concurrency ramps up, ToplingDB's tail latency is much steadier. For online services, P99 often matters more than the average. Speed is only half the story, the other half is cost. On the same data, ToplingDB uses about half the peak resident memory, nearly half the disk space, and finishes the full test suite sooner. One caveat matters here: ToplingDB's virtual memory size, or VSZ, looks high, but that comes from memory mapping and address reservation. It is not the same as physical memory pressure. RSS is the number to watch. RocksDB already uses snappy compression, shrinking from 27 gigabytes to a little over 6, and ToplingDB is still about half that. This slide is the foundation under every number you just saw. Performance comparisons do not mean much if the two backends are not storing the same bytes. So the benchmark validates them byte for byte. Record counts, total key bytes, total value bytes, and the overall checksum all match. Only after proving data equivalence do the throughput and latency results stand up. Let's summarize the takeaways. For throughput, ToplingDB leads across point lookups, batch reads, and the mixed RPC workload. For latency, P99 under high concurrency is generally lower by about an order of magnitude. For footprint, memory and disk are both reduced by roughly half. And about that exception, scan events prefix scans are faster on RocksDB because the hot cache test condition favors it. Blocks are already cached and decompressed. That is a property of the test scenario, not evidence that ToplingDB's scan path is fundamentally broken. It is also important to be clear about scope. HotStore is not a full node replacement and it does not participate in consensus. It is not validator storage. The current dataset is bounded, a range of checkpoints, not full history. A few details follow from that. Last seen means the latest occurrence inside the imported range, not the global latest state. The API layer is still a skeleton. The center of gravity is the database layer. I would rather put those limits on the table. Looking ahead, the near-term goal is to make the server-side comparison fully reproducible, fold the results back into the report, and clean up the demo materials. Further out, the roadmap includes a more complete API layer, deeper integration with Sui native storage, and a formal snapshot bootstrap path. The most practical next step is to run the 200 GB formal snapshot locally and use it as the main evidence for a larger scale test. What we have now is a solid starting point. One sentence to close: Sui HotStore is a key-value serving layer built specifically for Sui's read-hot path. Because the data is validated byte for byte, the RocksDB and ToplingDB comparison is credible, and under that condition, ToplingDB is better overall on throughput, latency, memory, and disk. We also explain the scan events exception instead of hand-waving it away. The code and related repositories are here. Thanks for watching.